We've done a lot of different force problems in this class so far this year. We, however, have not done that many with springs. So we're going to talk a little bit about springs. We start this problem like we start all other problems by identifying our knowns and our unknowns. Our first known is the fact that we have our force constant or a spring constant. We know that spring constants are K. All right, so our K is equal to our 2.5 newtons per centimeter. Right. The next thing we are looking at is the fact that at equilibrium, all right, so for our X spring initial, we have 15 centimeters. That's our resting length for our spring. The next thing we're looking at is the fact that we have the mass of the box. The mass of the box is then our 12.5 kilograms. Right? And this is a perfectly smooth horizontal floor. Because it's a perfectly smooth horizontal floor, we can go ahead and look at the fact that the friction is then going to be 0. Right? We then are going to delve further into the problem, looking at the fact that it starts from rest. And when an object starts from rest, we're looking at the fact that our initial speed is 0. Right. It then moves 96 centimeters during a particular length of time. Because it is moving 96 centimeters, we're looking at a change in x, right, of 96 centimeters. Right, and our time is then 1.6 seconds. We are going to end up using these last 3 bits of information to find the acceleration of our block, because this is force. If there is a net force, we are looking at an acceleration. All right, we have the fact that xf minus xi is equal to vit plus 1/2 at squared. All right. When we rearrange this equation, zeroing out the numbers that are 0, we then find the fact that acceleration is equal to 2 times delta x over t squared. We plug all our numbers in that we have, plugging in our delta x of 96, our time of 1.6 seconds, we find an acceleration, of 75 centimeters per second. Right? Because we had started off with our distance in centimeters, we do end up with an acceleration of centimeters per second, which is okay. All right? The next thing we are going to look at is the fact that we are looking at a net force in the system. We know that the sum of the forces is equal to the mass of our object times the acceleration. Right? Our force present in this case is spring force. Spring force is equal to K delta x. All right, remember delta x is equal to xf minus xi. All right, when we put this all together, we do end up, we're putting together this bit here with this bit here, all right, and we end up with the fact that m times a is equal to k xf minus xi. All right, we are ultimately looking for one particular value, all right, and that one particular value we're looking for is this xf, right? When I rearrange the equation with the use of algebra, I do end up with the fact that xf is equal to m times a divided by k plus xi. All right, so our xi was in centimeters, our k is in newtons per centimeters, our acceleration is in centimeters, so we need to make and our final answer is asking for in centimeters. Oops, I'm sorry. I seem to have lost some information. All right, there it is. Our final distance we are looking for in centimeters. Because of that, we are going to end up having to do some conversions. All right. We have the fact that K is equal to 2.5 newtons per centimeter. All right. What's the definition of a newton? Well, if we look at the definition of a newton, 1 newton is equal to 1 kilogram meters per second squared. Right? That's all fine and good and all that fun stuff, but it's not going to get us what we need. We're going to end up with the wrong units in the end, and stuff's going to cancel funny, and we're not going to get what we need. All right? So we are going to go ahead and to convert this 2.5 newtons per centimeter, right, into something that's all in centimeters. All right, so 2.5. Oops. Newton, nope, sorry, not newtons. kg m over s squared times 1 over centimeters. That's keeping track of the centimeters from the unit before. All right, how many centimeters are in a meter? 100. All right, so then our conversion factor in this case is going to be 100 centimeters over 1 meter. So we do end up with a number of 250 kg per s squared, right? Because we do end up with a lot of cancellations. If I do end up with a lot of cancellations, and if I go back, I do see that this centimeter does cancel with this centimeter, and this meter here cancels with this meter here. So we end up with kg s squared, which is perfectly fine. All right, so now we get to go to the fun part of plugging all our numbers into the equation. All right, so then our xf is equal to m times a, our m being 12.5 kilograms, our a being 75 centimeters per second squared. All right, our k is that number we just found. That's our 250 kg per s squared. And then we can't forget that last little number, plus our 15 centimeters, our equilibrium length. All right, when we get all that, we do end up having some nice, beautiful cancellations. Our kg cancels with our kg, our second squared cancels with our second squared. All right, so we have centimeters in our first term, we have centimeters in our second term. We plug this into our calculator, we do get 18.75. All right, and it does ask for 2 sig figs. When we round for sig figs, we do end up with an answer of 19 centimeters. All right, we can go ahead and test that. When we test that, I'm going to go ahead and our annotations will disappear for a second. Put in my 19, hit submit, and there we go. So that is how we solve a spring force question.